Okay, so we're going to do some computational examples now that we finished off 6.1. And so the first one will be straightforward, but I should also mention before we get started, you should also have the table of Laplace transforms in front of you. We're going to be referring to that. I'll write them down as we need them, but just in case, and just for practice, you should be referring to those. Okay, so let's take a look at the computing the Laplace transform of t squared plus 2t plus 3 sine of 2t. Right, from linearity, we already know that we can break this apart as the Laplace transform of t squared plus 2 times the Laplace transform of t plus 3 times the Laplace transform of the sine of 2t. Okay, and then from our table, we see that t to the n goes back and forth between n factorial s to the n plus 1, and that'll be the same. We'll use the same entry for t, and then for sine of 2t, we see that the sine of at is a over s squared plus a squared. Okay, so then now we can write down our Laplace. That's going to be, in this case, n is equal to 2. So, whoops. So the Laplace transform of t squared then will be 2 factorial divided by t cubed, s cubed, sorry. I'm getting distracted by the Microsoft Windows things happening around me, plus 2 times the Laplace transform of t is 1 over s squared, plus 3 times the Laplace transform of sine of 2t is 2 over s squared plus 4. Okay, so this is the Laplace transform. Good. Now, the harder part is probably going in backwards, so let's practice that a little bit. These are some exercises from the even problems in 6.1. So let's take the inverse Laplace transform of 4 over s minus 1. Okay, so we could write that as 4 times the inverse Laplace transform of 1 over s minus 1. And now if I look at the table, I see 1 over s minus a, and what goes over here, e to the at. And so in this case, the inverse Laplace transform will be 4 times e to the t. Okay, similarly, let's find the inverse Laplace transform of 3s divided by s squared minus s minus 6. Okay, now if I look to the table, I'm not going to find a nice polynomial like that. Instead, I'm going to have things of the exponential type over here. And so I notice also that this denominator factors. And so if, as a rule of thumb, if the denominator does factor, you want to factor it. And so let's just work with this expression here. I'm going to pull it out of the inverse Laplace for a second, because we're just going to do some algebra first. And so we get 3s over s squared minus s minus 6 is equal to 3s divided by, and then we'll factor it. Looks like s plus 2 times s minus 3, huh? Okay, and so at this point, I want to break it apart, and so I'm thinking about using this formula over here. So that means I'm going to use partial fractions. So partial fractions will give me a over s plus 2 plus b over s minus 3. Okay, so continuing with my partial fractions, multiply both sides by the denominator. A times s minus 3 plus b times s plus 2. So this equation has to be true for all s. Therefore, I can choose nice s's. For example, s equals 3 will give me 9 on this side. 0 plus 5b. So then b is 9/5. And then if s is equal to minus 2, that'll give me a minus 6 on this side. And then minus 5a plus 0. And so a will be 6/5, it looks like. Okay, so now we know, well, now we see, right, that 3s over s squared minus s minus 6 is equal to 6/5 times 1 over s plus 2 plus 9/5 is 1 over s minus 3. Very good. So now we're ready to take the inverse Laplace transform. And so this will be 6/5 times e to the minus 2t. Let me make that clearer. Plus 9/5 times e to the 3t. And so there we go. So in this case, again, just to remind us, in the case where we have a factorable denominator, we want to go ahead and factor it and use partial fractions to do the decomposition. Very good. Let's try another one, just for fun. We still have a few minutes left. Okay, let's try now to find the inverse Laplace transform of 8s squared minus 4s plus 12 divided by s times s squared plus 4. Okay, now again, if we think about it, right, I know if I use partial fractions on this, right, I'm going to have a over s, which is easy to invert, plus bs plus c over s squared plus 4, which I think I can invert. So let's go ahead and use partial fractions on this. And so before we actually do the inversion, let's go ahead and do the algebra. And so we have 8, I keep doing that, 8s squared minus 4s plus 12 divided by s times s squared plus 4. Do we remember how to do the partial fractions for this? We have a over s plus, and then this is an irreducible quadratic, so that's bs plus c over s squared plus 4. Good. Clear the denominators, and so we get a times s squared plus 4 plus bs plus c times s. And at this stage, we want to equate coefficients. So this is a squared plus 4a plus bs squared plus cs. So that's equal to a plus b s squared, right, plus cs plus 4a. Okay, and this leads us to 3 equations. We have one equation for s squared, one equation for s, and one equation for a constant. For s squared, we have 8 on one side and a plus b on the other. For the s terms, we have minus 4 on one side and c on the other. And for the constants, we have 12 on one side, 4a on the other. And so in this case, it's real easy to solve. A is equal to 3. So b is equal to 5, it looks like, and then c is equal to minus 4. Very good. And so now we can write, let's just go ahead and go back up here. This is equal to 3 over s plus 5s minus 4 divided by s squared plus 4. Good. Now, what am I going to do with that? I'm going to rewrite that as 3 times 1 over s plus 5 times s over s squared plus 4 minus 2 times 2 over s squared plus 4. Just to give you a chance to look at that. And the reason I'm doing that is because I know what the inverse Laplace transforms of each of these are now. And so if I invert the transform, I'm going to get 3 times 1 plus 5 times cosine of 2t, and then minus 2 times the sine of 2t. And there we go. And just in time. Alright, we'll do some more computations on the next video.